Right. Yeah.
Teaching-
That's the answer.
Teaching is a tough profession. It's
It's
a lot.
It's not fun.
It's there are times when it's absolutely not fun. First year is hard because I have to like create my lessons as I go.
And you can't just like...
Teachers that have been here for 5-10 years are teaching the same thing. They just show up and be like, "Oh, yep, we're doing this today. Here's my worksheets. Here we go."
Mr. Woodard being here for a whole 40.
Yeah. So it's tough first year teaching. Anyway, how did Friday go?
I don't know. It depends on that. Honestly,
We should probably go
Okay.
over that worksheet and find out.
Yeah, Mr. Sir,
You can't remember H.
Well, I could, but it's more fun to call you Mr. Sir.
I'm gonna take this
I
off, by the way.
honestly don't think I remember what it was over. I remember how to do forces.
It was
I
over
remember there was a car.
acceleration.
Oh wait, yes, now I remember. I remember there was like the clock thing. Yeah.
So one, it was unfortunate that it happened to be that we were starting a new unit the day I was gone. I didn't plan that, I didn't intend that, so I apologize. I did do that lesson, so I like introduced it still, right? I didn't leave it to the sub to like introduce a new unit to you guys. But this new unit, Unit 3, is about circular motion, and they throw in universal gravitation to that. They're similar, but there's just no other place to put it. So those are really the two topics for Unit 2. Circular motion is really cool. It's a really good unit. However, it's conceptually tricky for kids because, like, we've driven in cars. We've run on a track, like, you know, we do straight line motion a lot, and we understand it, but we don't actually experience a lot of circular motion. So there's not as much, like, life experience to think about, like, oh, yeah, I've done that before.
Like,
Now-
what would be a life experience of circular motion?
Well, one example is, like, in a car, yeah, when you turn to the left, it feels like you're getting pushed to the right. I hate centrifugal force with a passion.
Why?
It doesn't exist. It's a fake force. Whenever you turn to the left, you know how you're going to the right? You turn left hard, you get pushed to the right side. Kids always say, like, oh, the centrifugal force pushes you to the right. No, that's fake.
So then what
It's
is
not
it,
real.
What is it if you like have like water in a bucket and you don't like that real quick and
That-
then it pushes it back so it doesn't.
Yes, we're going to talk about that.
Water is
Do it.
still-
So what is that?
It's
called?
inertia and centripetal force.
What's the difference?
Centripetal. I'm getting a little ahead. Centripetal, the word centra, center.
Yeah.
That's a key part. Pedal is Latin for like seeking or like wanting. So centripetal
So
is
it'd be-
center seeking.
So it'd be like comparable to egotistical, self-centered.
Kind
I'm
of,
just
I
saying.
suppose.
When you start
Centripetal
spinning,
force
it's like
always
it's
goes to
one
the center.
thing.
We're going to learn that that's a real force. And then the other piece is inertia. If you have that water spinning in the bucket, it wants to go straight constantly, but the bucket is always pushing it in. That's what keeps it in the bucket the whole time. So anyway, we're getting ahead. I'm going to
So, like, if
build
the
up to
force
that.
is trying to push it out of the bucket. The bottom
No,
bucket is
there's
soft.
no force pushing out.
No, like,
nothing's
it's like
pushing
it's
out.
Pushing it to the bottom of the bucket.
No. Nothing's pushing it to the bucket. It's inertia. It wants to stay in its motion, right? I spin it. It wants to go this way, but the bucket's constantly turning it.
I see.
So its inertia wants to stay in its motion, but it's constantly getting pushed inward. That's why it seems like it sticks to the bottom of the bucket. It's because it's always being changed. Anyway, I'm going to lead up to that, but you had asked, we're going to circle back and explain that more. The first thing I need to do is the test. I need to pass those back. I have, let me put this on. Joey, wait, no, that's not yours. Yours was. I thought I had another sheet for you, but that's not it at all. Maggie. John, what announcement did I hear about you this morning? Tennis?
Made to regional thing, cross country.
Cross country. I'm sorry. I just heard your name. I was like, oh, I know him, and then I missed the announcement.
Our tennis team was good enough to go.
Ethan, you play tennis, don't you?
Yep.
Okay.
I'm just kidding, Ethan.
Aiden. Well, congrats. So regionals, how close is that to like state? The
Uh,
regional, district, regional, state?
No, it's regional and semi-state.
Okay. Nice. Well, that's awesome. Congrats.
So we're going to state all the teams are terrible.
Joey, Jaya, Ethan.
You guys don't win state next year.
Josh.
Oh, we won't win state.
Cody, how you doing? Hustle.
We're gonna get there.
You're gonna get there.
Okay, John's gonna win state next year. John is gonna win state next year.
Oh, I don't have my pen.
Oh,
You got these up? Okay, thanks.
Annoying.
So,
Yeah, I know.
I don't know if you knew that or not.
Yeah, I know. That's all. Okay.
knew I left something at home.
John is going to get held back.
All right, guys, I need you to bring it back, right? I guess I want to open up the floor to what questions do you have about the test? I'm really mad I left my physics binder home. I had my answer key.
Why didn't I guess it?
I have the answers that I used to grade it, but not my work. So that's frustrating. What questions do you have? What are ones that you want to be like, hey, I didn't get this one? Or like, wait, how was I supposed to answer this one?
There was only two that were back.
What can I review or help clarify?
I don't think you have enough time.
Yeah, you got more right. Is it bad I would have got more right if I just answered randomly and we did true, false, true, false, true, false, true, false? I would get more.
I don't think I intended to do that.
Okay, I thought you did maybe just to, like mess with us.
No.
You don't put on you.
That'd be a bold thing to gamble on. Like, I think he did true false. I'm gonna just go with it. That's a bold move.
Now I have heard of like people like a teacher making a test that like the answer is A for all of the questions.
Mm-hmm.
Just to
To psych kids
Yeah,
out.
to psych kids out and make them confident. Can you imagine being that one student who just randomly just goes, "Oh, I don't know what this test is about." A.
Yeah. Anyway,
Imagine being the
okay.
kid who always marks B, though.
Andre, I need you to get your phone away, please. Thank you. All right, my question was, what questions do you have about the test? Is there anything I can explain or clarify?
How about we redo the entire test?
I don't have time for that. I want to know if there's ones that you really didn't understand, or I can't remember which ones. I wish I had my copy of the test.
How about we go over question 30?
Okay, what was 30?
30.
I'm sorry, I'm not there. Oh yeah, the ramp.
Go over question 23. Then go over question 21, 23, and 30. 21, 23, 30. 20, 21.
Well, you also said 23.
I underlined a couple that I genuinely had lived through. That was
So 20, 21, 23, 30.
Okay. So which one did you want to see?
20, 21, 23, and 30.
Again, we can do a couple.
sounds like the ones that started dirty.
If you want 30, I can start with that one. We'll go to the bottom. I had one you could have borrowed.
Now I would have no idea what this one was. This I'm not guessing.
Actually, this one I think I took from the notes. I say that all the time. So 30 was the finding the coefficient of friction. So if this ever opens up for me. Come on, computer. Yeah.
I mean, a little bit. Why is there something that you can say?
that would concern you if I knew? There's some information that would be scary that you would not want to know. You were bothered about it or not.
Situation wipes.
I did not maybe see that or think, nope.
What did he say? Nothing. Wrong. Obviously white.
Can't remember which slide I pulled that question from.
19 million is better. Should have had you post.
You hear what he said.
I chose. No.
Okay.
You already said it?
No, we didn't.
I don't know what happened. What Andre said?
Okay, this one is 21, 23.
You're Caucasian.
May I double check it?
Wrong because you're obviously
False.
Yeah, right? This problem was 23. What's the magnitude of the perpendicular force? This guy. All you got to do, if the weight you know is 75, that's the actual force. It's at an incline, so you got to break it up into some part goes down the ramp, some is perpendicular or normal. So all you need to do is realize I got a triangle. This is my hypotenuse. And if I do cosine of 27, right? Cosine of 27 is adjacent over hypotenuse. I know everything except the adjacent, so I just solve for it. That's the magnitude of this blue force, which was 67 pounds.
and I told you what to do.
Then all you need to do is do the other way. Sine of this is opposite over hypotenuse. I know everything except the opposite. Well, I just solved for it, and that was 34 pounds. So the answer was like A, or the first option. So that one I meant to just have you see that there's a triangle and use your trig to find the components of the actual force.
And I told you what to do.
All right? The 30, what'd you say, 30? No, 31.
No, I said 30.
Oh, 30?
13.
Oh, yeah, 30 was from...
Yeah, so 31 I guess I got it right. 31 I got 30.
I'm not
I guess I
encouraged
got it
by the
wrong.
fact that you're
31.
guessing.
31 I got wrong from guessing. 30 I got wrong. No. Yeah.
Yeah.
I got 30 wrong and I got 31 right, and I guessed on both.
You got something.
So this one,
You got both right.
guys, this question was also from, we had talked about this one. Question 30. The truck's rear suspension needs to have no more than 10 inches of displacement. If the maximum payload of the truck is 5,000 pounds, what spring constant should that engineer choose? Right? So what you need to realize is the total suspension cannot be displaced more than 10 inches. Right? So I'm going to put, so right here, from here to here is 10 inches. I'm going to use my worst case scenario to design my suspension. What was the weight of the payload?
That hay bale weighs 5,000 pounds or something.
So 5,000 pounds
Yeah.
needs to be distributed over 2 shocks. So we need to use Hooke's law. Force of the spring equals negative kx. Well, what force does one shock need to support? 2,500. You had to understand a car has 2 springs. So this should have been 2,500 lbs, negative k, that's what I don't know, and 10 inches. Then you literally just plug it in and solve. You had to realize you only do one side at a time. Unless you did it together, you did 5,000 over 10 inches, your k value would be total. It would be the 2 springs working together. So you'd have to realize, okay, when they're working in parallel, the total k value is split between the 2 because they're working together.
So I got this question wrong because I don't know crap about cars.
No, it had nothing to do with cars,
You
right?
have to know there's two suspensions. I didn't
It
know.
has to know the
Each wheel has a suspension.
I thought we've had this conversation.
Yeah.
Haven't we talked about this when I did the example?
I remember
Like, we
mentioning-
solved this problem.
Listen, my memory is absolute crap.
Yeah, I did.
Like,
It
it's
wasn't
gotten
a
that
trick
way.
question like how you have to know cars. It was because, like, we literally did this one. So I threw it back on there. And it's also an application. I don't want to just have, like, random physics problems. Like, I want you to see that we use physics. Like, there's a purpose to it. It's not just this academic thing we know. So this one would have come out to, what was it?
150 pounds
250.
for each frame.
Yeah, 250 poundage. Pounds per inch was the spring constant.
But on this one that we did, it was 500. No, sorry, 250. My bad.
Yeah. This question, I changed the 3,000 from the problem that we did. We did this problem in the notes.
Yeah.
All right, is there another one that I can show you?
21.
21. Gosh, I'm so mad I don't have mine. Because I did an answer key with. Okay.
I'm thinking you're a B guy because I swear like 50% of the answers is a B. 21 is
Yeah, a lot of the questions I got wrong is because I didn't put B.
Yeah, that's what I'm saying. I should have guessed B. I probably got a better score.
I don't see a lot of.
Remember this?
Was this it? 100? Yes, this is, again, I pulled this from the notes too. So this is when you have a 100-pound box by 2 strings. It's hard to tell, but this angle is 10 degrees. Whoa, whoops. 10 degrees. I want to know the tension in that string. So I'm going to draw here's my force. The tension is pulling up. I want to know this component and that component, and this angle is 10 degrees. You see that?
Mm-hmm.
So the thing you need to realize is if I have 2 ropes, they each support half of the box. They're exactly the same angle, so each string in the y direction is 50 pounds. That's the only way that 2 symmetric strings can support 100 pounds. It's in equilibrium. The positive y force needs to equal the negative y force. There's no motion, or I should say there's no acceleration, so there's no net force, so this 50, basically like this, 50, 50. Well, on one string, that's 50. Now I have enough to just do a simple trig and say, I want to know t. So if I do cosine of 10 is adjacent over hypotenuse, t equals, I don't remember what it was, 78 or, can someone tell me?
280.
288? Oh yeah.
The answer.
So if you have 2 strings at 10 degrees, each string has to be pulled at 288 pounds in order for them to both support a simple 100-pound box. That's because you have to be able to pull it this way and up, and this force needs to balance to hold it up. Well, you need to add those together, right? A squared plus b squared is c squared. That's why that tension is so high just to hold a 100-pound box. So that one you'd split in half and do half a problem. Half the weight. Any other questions?
20.
20? I'll do a couple more and then I want to...
I figured out 20.
Oh, 20. This one I made up.
Does F equals
Big old aircraft.
Is that a AC 130?
Might be. I don't know my planes hardly at all. As a kid, I liked the B-2 stealth bomber.
It's definitely playing from H to fuel.
An aircraft carrier.
Yeah, this question. So this one, 50,000 kilograms, needs to go 270 meters per second before it takes off. A million newtons of force.
Actually, got this question. F equals M.
What is the aircraft's acceleration? John's got it. F equals ma. I want to know the acceleration. What's its mass?
Yes.
50,000. What is the force that this aircraft is capable of applying?
1 million.
1 million. And I'm forgetting units, sorry.
Thank you.
Sloppy. Boom, that's all I need. F equals ma.
You ever had
I need the acceleration, so I just divide out, solve. The acceleration was, I think it was 20. 20 meters per second per second. Again, I had told you guys that question I left off, the per second. So that was my typo, but I corrected that. That was my bad. Does that one make sense? That one I wanted to be just F equals ma. You know the force, you know the mass. I'm asking you to find what's the acceleration, Newton's second law.
Why'd you highlight that?
Huh?
Why'd you highlight that?
Oh, it's because that's what's selected.
Right.
The check mark is the correct answer. The
I
key.
know, 'cause, like, you highlighted
Aiden, you
that
got one
like,
you want to look at?
Yeah,
Since
number
Marcus,
2. Why did I? No, actually,
You got it?
I was just.
You were yeah. These were at the beginning. I started with like conceptual questions. Like some of them were just definitions, but the more massive an object is, the more acceleration it experiences for a set force. Well, that's not true. F equals ma. If I keep my force the same, but I have more mass, my acceleration has to go down. So it's the opposite. The more mass of an object, the less acceleration you have from a given force. Right? And a great way to demonstrate that is showing like the size of the letters. Right? If this has to be the same, the average size of these have to be the same. If I crank one of them up, the other has to go down, so that they still average to the same force. And that was when we did Newton's second law. We talked about there's some relationships. More mass for a force, less acceleration. Less force causes more mass. The only way you can increase the acceleration for an object is more force. The only way you can have zero acceleration is zero force. Things like that. All of them come from F equals ma. Any other questions? No? Okay, so again, I got those inputted. Virtual students' years I put in there as well. Everything is in Power School, correct?
Yeah.
I think I got everything in the Power School. Google Classroom I don't use for grades. I just see them and then I immediately transfer them to Power School. So that was that. So I want to switch force, or not forces. I just read the word force.
We're gonna go over that paper. See if we did it right.
Oh yes. Freaking left it at home too. Dang it! I took my binder home, my AP Physics stuff, because I was going to do some lesson plans. Didn't even get to that. And then I left it. So then I don't have my test key or the answers. But I know how to do them. So what we can do is we can talk about, actually I'll throw them up here. So again, it was 3A and 3B I had you guys work on. It's okay if you didn't get 100%. I will finish those concepts.
Also, does that mean we're abandoning the rest of this other unit?
Yes, a lot of them would have been helpful for Unit 2. We didn't do a lot of them. hold on to them. Don't throw them away, because when we get to start prepping for the final test, we can kind of go back and do some of those to practice. It was just I didn't want to keep doing all of those when I was able to find ways to do those in person or talking about them. And dynamics, I know enough that I figured that one out. So what I want you guys to do is get out, it's 3A, 3B. Where is it?
Hope I did it right. Where is it?
So we'll go over that together. Oh, come on. All right, so 3A was called inertia and acceleration. So this is one where you need to start thinking about, again, kinematics is motion. Dynamics is the forces that are causing the motion. You need to start putting these together, and we're going to start applying them into a new topic of circular motion. In this case, it was still straight line. This isn't a free body diagram. This is just a rough sketch of what's going on. I'm going to take this stupid thing off. So we got velocity, acceleration, and net force that we have to draw on this car in this scenario. The scenario is Angela is in a stop car at a traffic light when it turns green and she accelerates. First question, what's her velocity? What's the velocity of the car if she was stopped and the light just turned green?
She hasn't moved yet. That's just figured.
Yeah, she hasn't moved yet. V is 0. There is no velocity vector.
She was doing a burnout and she just dropped the brake right after that lap, like right at the second turn green.
Then we would look at the split second that she lets her foot off the brake or something. Like 0.0 to infinity and then 1 seconds. Again, you have to, we simplify physics, right? But as soon as you get past like that 1/10 of a second, you're right, there would be motion. But we want to know, like the moment it turns green, she has not moved yet. Is she accelerating? Says she did. So she's hit the gas. She started to accelerate. Where's your acceleration vector? What direction is her acceleration going? Forward. She hit the gas pedal. We're just going to draw A for acceleration. That's the direction that I'm accelerating. Where is her force being applied? The force causing the net force on the car. Where is that force being applied? What direction? Is it going this way? Is it going backwards? It's going forward, right? F net. This has to be true. You cannot have an acceleration and the net force be in different directions. You would break Newton's second law. And you would also break physics. We can't do that. So that should make a lot of sense. The question is, which way does Angela's body feel pushed? If you're in the car and you just stomp on the gas, what do you feel in the car? You feel that you got pushed backward. Good. Does everyone understand that? Does everyone experience that? Like your mom or dad or somebody in the car, they just turns green and they just stomp on the gas and you get thrown back in the seat. You feel this push backwards. So what you feel, why is that? Do not say centrifugal force. One, it doesn't even apply because we're not in circular motion. And two, that's a fake force.
What's the other one that starts with a C?
Centripetal, but
Yes.
that's circular motion. We haven't really got there yet. John, what do you think?
Her body wants to stay in place while the car is accelerating because of her inertia.
Yes, bingo. John nailed it right on the head. She feels pushed backwards. Her body is at rest. It wants to stay there. All of a sudden, this car is accelerating and moving forward. Well, if her body is at rest and the car goes forward, they slam into each other, and she feels pressed back into the seat because it's trying to shove her forward. She feels pushed back because she's trying to stay still because of her inertia, but the car is also trying to move her. That's why you feel pushed backwards. It's exactly right. Basically just her inertia. Wants to stay at rest. Does that make sense? Good. We're going to use all these topics, things that we're learning. Some of them are separate, but we'll use them, right? We use inertia to continue to do physics and dynamics. All right, that's a great one. So now, let's up the ante a bit. Do the second one. She approaches a stop sign. Oh, this one isn't. Not quite at rotation yet. She approaches the stop sign and slams on the brakes.
Someone's a bad driver.
Yeah. Where is her velocity going?
She only knows how to stomp on the toes.
No.
Maybe she
Forward.
Yes, she's going and she's seeing a stop sign and hitting the brakes. So she's still moving forward, but she stomped on her brakes.
Well, those things on the hood of the car are supposed to be like lights.
They're air ducts.
Because they kind of look like deformed toes.
Yeah, some cars have
so
lights
she's a
up like
bad
that.
driver and she has this nice of a car.
All right, let's. We're like making up stories about the physics question.
Wait, so if that's like vent, so what is she driving like a
All right,
GT?
all right, we need to focus. That's her velocity. If she hit her brakes, what direction is the force of her brakes acting? Backwards. Good. When you hit brakes, you oppose motion. You're applying a force in the opposite direction that you're traveling. It's called slowing down or decelerating. If the force is acting this way, without even thinking about whether it makes sense or not, which direction does the acceleration have to point? Backwards. Newton's second law, the net force, F equals ma. Mass is a scalar, so the force and the acceleration are vectors. You can't say that vectors are equal if they're in a different direction. You would break math at that point. We're not breaking math or physics today. So she's hitting her brakes and applying a force and causing an acceleration backwards. That acceleration is slowing her down, decreasing the velocity. Which way does Angela's body feel pushed? If you stomp on the brakes, what does your body feel like it's doing? Getting launched forward. That's the reason seatbelts exist. Feel pushed forward. Which way is the car accelerating? Oh, dang it.
Backwards.
It's accelerating backwards. Which direction is the net force on the car?
Backwards.
Backwards. This is my ditto sign.
Negative.
Again, John mentioned it's her inertia that causes this fake feeling. Her body is moving forward. She hits the brakes and the car slows down, but no force has started to act on her yet. So she's going to feel like she keeps going forward until something acts on her. Well, that something is your seatbelt.
That's something that's the steering wheel.
Your seatbelts are the reason that when you get in a collision, you don't ram into your center console or get shot out your window. That's what would happen if your inertia was left to do what it's going to keep going at whatever speed you hit the wall. That's going to cause a lot more damage than if you have something restrain your body and apply that force to slow you down. So that's what's happening here. Now we're going to get to circular motion. We're getting to get to a little bit of new stuff, but you've probably all experienced this. Angela continues driving. She rounds a corner. It's at a constant speed. She is not accelerating. She's not hitting the brake. She's just coasting at 30 mile an hour, which actually is a very fast speed for a turn, but regardless.
We've already established that she's a bad driver.
Yeah, so we'll stick with 30 mile an hour turn. She's a reckless driver.
Maybe she's
But
just
constant speed. You need to think,
she's a really good driver.
where is the direction of her velocity
She's in the street.
at this moment in time? Where is her velocity pointed?
Direction of the car.
Direction of the car. Good. Remember I talked about tangential velocity? She's going in a circle, but her car is moving linearly. It's just that the direction of that line changes constantly. At any moment in time, the velocity, the tangential velocity, is perpendicular to curve, or in this case, in the direction that the car is going. That's her speedometer is telling her it's 30 mile an hour this direction. Acceleration.
That's a little harder.
She is not accelerating this direction.
She's not accelerating at all.
Incorrect.
Well, you said, like,
When she hits the
I
curb.
said she's not accelerating in this direction. And I say that because it's constant speed.
She's accelerating.
If it's true that she is not accelerating at all, she would be going like this forever. You need to remember, velocity is a vector with a magnitude and a direction. If she turns a corner, she may not be changing the magnitude of her speed, but she's changing the direction. Anytime you change motion, that's acceleration. So you have to have acceleration and a force. What direction is she accelerating? This way?
Yeah.
So like this?
Yeah.
Good. I touched on this in the video. We're going to talk about it in detail today. But I mentioned in order to rotate in a circular motion, you have to accelerate towards the center. This is centripetal acceleration, right? Her motion makes a circle. The acceleration that causes circular motion always points to the center of that circle. If my acceleration is in this direction, where does my force have to be pointed? Don't even think about what makes sense. What do you know the force always has to be? Same as the acceleration. Newton's second law. You could have absolutely no idea what's happening, but if you see that there's an acceleration, you immediately know what direction the force is in. Rather, the net force, the total force, causes acceleration. So we got the velocity, the acceleration, and the force. Which way does her body feel pushed? You're driving, your maniac friend or whatever just cranks a hard left. What does your body feel like it's happening to it?
The other
Feels like you get shoved to the right, doesn't it? You might hit your head on the window, right? Feels pushed
Yeah.
to the right.
Doesn't believe the stop sign either.
Do you guys understand this? Like, have you experienced this?
Yes.
When you turn left, you feel like you're getting shoved the other direction. Which way is the car accelerating? There's a couple ways you can phrase it.
Left.
Left,
Counterclockwise.
inside of curve,
Counter.
center of turn,
I think we'll go left.
turning, circle.
Let's go with left. We'll go.
Okay, as long as you have the picture and understand,
Wait, counter.
left is immediately to the left of the car.
What about counterclockwise?
Yeah, that'd work.
Okay, because I know that's what I do on the next page, so I know if that would like. have still
Yeah,
work.
that'd work.
Okay. That's what I said.
Does this make sense?
Yes.
Direction of the net force? Don't even need to know the question. Acceleration and force always in the same direction. Rather, the acceleration and the net force. I could have two forces, but whatever the net, the total, that causes my acceleration. Does this make sense? I guess a key thing I want you to understand is this car is not accelerating its speed. It's a constant speed. But because it's turning, I'm changing the direction of my speed. My velocity, I should say. That is acceleration. This is a concept that most kids would get wrong. Every time you turn a car, you are accelerating. No matter what. If that's at a constant speed, your acceleration is just turning the car. Now, if you're hitting the gas while turning, you have two forms of acceleration. You have a tangential acceleration and the centripetal, the part that turns you. So just know, I could ask a trick question, say, Timmy travels at 50 mile an hour around a bend. Is he accelerating? You would say yes, because he's turning. It's around a bend. Right, Josh?
So, and you already said this, and I'm just really wrong.
That's all right.
In the way thing, but
Go for it.
is it because like you'd be accelerating in the turn because your inside tires would be going like slower, and your outside tires would like speed up to catch up with them?
That's a part of it.
I don't know if that was the reason why, because that's kind of the way I was thinking of it on how to be accelerating. Like, yeah,
That's part of it. The other part is your tires have friction. When you turn your steering wheel, you turn your friction in a new direction that starts to go to the center. Now, some of it keeps pulling you forward. Some of it points to the middle of your turn. But you're right. I think I put it later in the slides, and I'll show you. But every time you turn, your inside tires turn less than the outside tires.
Yeah.
And your car has something called a differential that lets that happen. It's really cool, especially I'm a car person. I'll show you that. I have a really cool video that shows you like the inner workings of it.
Or if you're really good and you're in band, you would know from gate turns.
Oh, nice. Right?
Wow, what a loser.
I have no idea about band, but I understand enough to...
Like a gate turn, like when you're marching, you have to like the inside people
Yes,
march slower.
that's exactly right. Yes. If you have a line of people making a turn, the people on the inside are going to do like little baby steps,
Yeah.
while the people on the outside are going to be like trying to keep up. That's exactly right. Yes, that's good. All right, let's get through this. Speeding up or slowing down, or constant speed?
Constant speed.
Constant speed. Right?
Yeah. Yes.
Turning clockwise, counterclockwise, or not turning?
Counterclockwise.
This acceleration is going to cause it to turn this way. That's counterclockwise. Right? Oh, eventually we're going to get to the right-hand rule. That's really cool. All right, second one. This one down here.
Speeding up.
Speeding up.
Speeding up.
Right? There's some component of this acceleration going this way, some going this way. This component speeds up your velocity.
Right.
Speed up. You also have another piece of acceleration, another component. What does that component cause you to do?
Turning counterclockwise.
Turning. Again, acceleration goes up. My turn looks like this. That's counterclockwise. That's what CCW and CW. Good. Newton's second law all day. This one.
Constant speed.
Constant. There's no acceleration in the direction of the velocity,
Not turning.
so you're not changing the magnitude of the velocity. You are changing the direction, aren't you?
Oh, so
You're turning clockwise.
Be careful. Yes. Her motion is going this way, and the acceleration goes up. So my center of my circle is this way. This is clockwise. She's basically driving in reverse.
Yeah.
Again, further proof that whoever this person is, they're a bonkers driver.
Or maybe she's just really, really good because.
Hey, that's true
because
too.
if you watch like Fast and Furious, you really think like they don't necessarily drive in a safe way. They are very good at it.
It does look like a. Neither does Mater. That's good. I love when he says that. It's like, how did you do that? He's like, rear view mirrors, and he like flaps them. All right, last one. Speeding up, slowing down, or constant velocity?
Slowing down.
Yes. Some component goes this way. Some component goes this way. This component, that's changing the magnitude of my velocity. It's decreasing it. So, slow down. She's finally getting some sanity.
Clockwise. Dang.
Counterclockwise. She's moving in this direction, but there's some acceleration that is turning her. This creates counterclockwise. So CCW. We follow that? We see we can have a weird acceleration, break it up into components. Some component is going to be tangential, whatever motion the vehicle is, that linear part. The other component should be towards the center of your circle. That's the centripetal component. Right? My acceleration vector is doing two different things and causing two different types of motion. All right? So now what I want to do, did I have it up? Nope. I think I want to try and finish this slide. I can't remember where we got to in the video. Do you guys remember? I think we got through this, didn't we? This is another thing that you're talking about with the track. And I mentioned this in the video, the head start. So in this scenario, all of these objects are moving at the same speed. If they're cars, they're all at 20 miles an hour and just coasting. But look, their circular motion is very different. Same velocity, but you have, I think it compares here to here, maybe here to here. Twice the radius. Which one is a larger distance?
The bigger one.
The bigger one. So if I can move at 20 miles an hour, but I got to go a lot longer distance, who can complete a circle faster? This guy, look at that. He's literally, if you started any track race in a line, whoever's on the inside would almost absolutely win. The outside person would have to be so much faster than the inside person to start at the same point and complete one revolution at the same time. They have to run farther because your radius is bigger. So if they have the same speed, what happens to their angular velocity? Angular velocity is how quickly you're completing a revolution. Who's completing a revolution faster? Green, red, or blue? Green. This angular velocity is the highest. So the outside has half the angular velocity. Right? They're running at the same speed, the same tangential speed, but they're completing a revolution slower because they got to travel farther. Again, that track example. Okay, if we put them all on the track, they're all on the same lane. It's fair. They complete the same distance. It comes down to who runs faster. The tangential velocity. In this case, whoever can run faster can finish the race quicker. Yep, but they're on the same lane, right? Remember I gave you the example in track, they stagger the starts because to keep it fair, the people on the outside get a little bit of a head start because they have to run a farther distance. That's why they do that. Race cars. This is a really weird example. If you have two cups end to end, they don't roll down a ramp steady. They're super wobbly. If you do them inside to inside, it's even worse. They use this idea to make trains. On a train track, this lip sits inside, not outside. It's because it keeps it stable. As soon as it moves, it hits the inside and is steady. This is just a random side note. Here's a good one. What happens to your speedometer if you get bigger tires and don't get your speedometer adjusted?
It makes it inaccurate.
Yeah. So stock wheels are 29 inches. It counts one revolution. It knows how big your tire is, and it calculates, okay, if I'm going this many rotations per minute, I'm traveling at this linear speed. It just does the math. If I change my tires and I don't adjust the speedometer, it'll say, oh, you did one revolution. You're going this speed. Well, wait a minute. One revolution is more distance. It'll only count one revolution. So when it reads 65 on the bigger tired Jeep without any corrections, are you going faster or slower than your speedometer? Faster. It counts rotations. If I have a bigger tire, one rotation, this is a bigger circumference. I'm traveling farther every rotation. So I'm actually speeding constantly.
Technically, the bigger tire you have, the longer it will take to wear it out because it's the tire is even less wear on it. That makes sense what I'm saying?
Oh, I get your
I worded
logic.
that very poorly
No, I understand.
because you can
However,
go a lot longer distance.
You have a smaller contact patch because you have a bigger tire, or you're distributing your weight over a bigger surface. There's a lot of weird things that go into it. But I like your logic. We'll just leave it at that. We can talk about that later. Okay, this is getting to the differential. What's scary about if this is my actual tire and that's my spare tire? What do I not like about this scenario?
Everything.
It's tiny.
It's tiny. Why is that a problem? Why is this an issue?
Because it's going to be moving at a different,
You're going to have a wobbly
like
car.
one revolution for it is very different than one revolution for all the others.
Bingo. This tire is the same size on the other side. How do I get a big tire and a little tire? They're literally connected. How do I get them to rotate at the same angular speed and cover the same distance?
Real fast.
Huh?
He's got to move real fast.
This guy?
Yeah.
Yes. This tire can cover a lot of distance in one revolution. This can only cover a little bit of distance. So you're this is horrible for your car. It's bad for your differential. Your differential lets you turn, and it lets the inside wheel rotate slower than the outside. Because the inside wheel's only got, remember the inside of your racetrack? The inside is a little bit of distance, the outside's a lot. That's normal. Your car can handle that in turns. But you're basically doing that constantly. This wheel is going to have to spin like crazy just to keep in line with the other wheel, which is rotating normally. This is where your differential comes into play. This is a schematic. I don't want to dive into it, but I want to show you. There's actually, hopefully this will play. This is from like the 1930s. Oh, is it blocking my video? You hunk of junk. Oh, enable content. There. I have internet. This is an awesome video, by the way.
GM. Wow.
There's a bunch of... Oh, here.
The man on the outside has to ride a lot farther and a lot faster in order to keep up with the parade.
There's your band
The
turn.
outside wheels
That's exactly
must spin
why.
faster than the wheels on the inside because they have a greater distance to travel in the same length of time.
All right, I want to show you the differential.
One or the other
You see this?
has to slide. So
If
engineers
the
have
wheels
to
are
find a way to
stuck on a
connect
metal
both
pole,
rear
the
wheels to the
inside is going
engine
to have to slip
without sliding and
while the
slipping
outside
on
wheel
turns.
keeps traction.
The
The
device
car
which
can't
makes this
be
possible
slipping on the
is
inside
a part of
constantly.
the rear axle. It is called the differential.
The differential.
Because it
So they do a
so that they can
demonstration.
revolve freely at different speeds.
If you put these together,
Let's get something to hold this bar in place. This is fine. As
that's
long as
driving in
both
a straight
wheels are
line.
able to
They
turn
all
at
rotate the
speed.
same speed.
But let's see what happens when we go around the corner. With this arrangement, we cannot drive one wheel faster
see that?
than the other.
If they're trying to turn slowly on the inside,
And if we stop one wheel,
it restricts it.
we can turn either wheel.
So this is where
We
your
need another
differential lets it
crossbar
turn.
and more spokes.
If
to
you have a
carry
bunch of
on
these
the job.
spokes,
Spokes of the freewheel around.
you see that?
As long as both wheels are free to turn,
They've locked the inside
the
wheel.
bars do not swing up. The crossbars will continue to push
You see how
the
it
spokes
rotates
of the freewheel
twice?
around.
It'll let your outside wheel turn while
As
the
long
inside
as
is
both
stuck.
wheels are free to turn,
That's what your
The model
differential is
for
doing
use in an
all the time when
automobile.
you turn.
we will have to make a few changes.
What if I do a bunch of spokes?
More continuous action. And changing the shape gives firm, constant contact. Now we can make the gears thicker and stronger. And we have differential
Yes,
gears.
yes.
The edges are
Yeah,
cut.
they're
so that
like
they will
locked
fit
together, so
more
they
smoothly
only
and
turn the same
silently.
as each other. So if you try to
And
turn
another
with a
gear is
locked
added
differential,
to share
your
the work
inside
of
wheel will
driving
like
the axle.
skip and stutter
The principle
because
is the
it's
same.
it can't turn the.
In order to turn
It's
the
turning
support
too much.
and drive the wheels,
So this is what a
we can
differential is
fasten
doing.
a large gear.
It gets really complicated.
Notice that the power is
Gets into a lot of physics,
this way.
automotive
Today,
engineering.
Engine it out of the way.
Again, your
And
car
the drive
uses
shaft
very
is
simple
connected to the rear
machines,
axle at the
simple
front.
ideas,
The new low
but it
center
does them all
drive
together all
makes
at once.
The rear axle quieter, stronger, and more durable.
Yeah, it's really cool.
Because
I just
it
wanted to
gives
show you the
better,
application
smoother
of
contact
like an engineer.
between the gears.
Like Brody and Trevor are in my engineering
the
class.
automobile of today, with the low
They would
center
know,
drive,
understand
is
physics
stronger
in order
and
to be able
more
to design that car's
Every
differential so
part
that it
of
can
the
work.
rear axle has been built to withstand.
That's why science isn't just meaningful or meaningless. We actually do it to use stuff.
Design a car.
Has anybody heard of the Coriolis effect?
Yes.
This is a really cool video.
I've heard of it, but I don't know what it is.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion. Right, here's the game, right? You're going to throw the ball straight. So what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it, all right?
see how well they can do this.
Right, what's going to happen, dude? Oh, it's going to veer off
Also,
to the
this
left.
is sweet.
So the
It's
ball
like
is going to swerve off to the
they
left.
put like little
Yep.
chairs
And
on
you might catch it,
so that you can
possibly.
like sit
Okay,
towards
good.
the center.
Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
To the ball.
What a pompous guy.
The ball will be thrown straight across the spinning merry-go-round. But where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
Who's going to catch the ball when she throws it straight out?
Right, in your own time, throw the ball!
I got this.
Even though she threw it straight.
So, the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw? Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, it did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
No
They
idea.
do a
It's
nice
called the
diagram
Coriolis
of that.
effect.
It's
And it's very simple.
it's
It's
an optical
objects
illusion.
in motion
It really messes
appearing
with
to
your
be,
brain.
it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight. It's still going straight, but the table is moving below you. And all of a sudden, look who's in front of that straight moving ball. And it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to. And that, ladies and gentlemen, is a Coriolis effect.
What would happen if she threw it to the person to her right?
Yeah, what did she counteract?
It comes back
It would come back to her.
What if she threw
Because
the
she would
person to
throw
her
it this
left?
way, and then she would rotate and
Finally.
What if she thinks the person to her left?
It would go to the person across from her.
It would go for the person across.
yeah.
So you can counteract.
Yeah, she threw it left.
It would go to the person across.
So
Yeah.
for
It's
science,
it's an optical illusion. That's why it's so hard to
what
understand.
day do we take our all-in-all test for AP? Or AP test?
Oh, May 5th?
All right, so on May 6th, can we construct a gigantic merry-go-round out there?
If you guys bring the materials, we could
And
build
then
it.
we'll all start
I got a
spinning
drill.
a silent ball on the giant merry-go-round.
We can try that.
Yeah, that would work.
You get some massive bearings. And a big clap.
All right, and again, I want to touch back to, you guys saw these equations, right? These are on your, Meg, do you have your equation sheet? So if you guys look at your equation sheet, you can see all these equations, they show up kind of in the middle of your equation sheet, right? They're the same as our velocity equations, right? V equals V naught plus AT. That equation is exactly the same, but you use angular velocity, not linear. Angular acceleration, not actual acceleration. The equations are, exactly the same. Theta is how far you've rotated, your displacement. Angular velocity, angular acceleration. I want you to point out all the equations are the same, right? Theta is theta naught plus omega naught t, 1/2 alpha t squared. Omega equals omega naught plus alpha t. And this one is not on here, but you could just look at this equation on here and say, like, okay, if I replace linear variables with angular variables, it's the same thing. So I want to just point out the equation sheet. It has almost all of them, but they're the same. So motion happens the same. The relationships are all the same. It's just not in a straight line anymore. It's in a circular motion. Right? So I want to get a brief start on the next slides, which is really we're going to dive into that centripetal acceleration. I kind of already told you this. Which one of these represents centripetal acceleration? In, out, or tangent?
Out.
Centripetal, remember, is center seeking. Which one of these arrows seeks the center? In. That's one way that I always remember. I know centripetal is center seeking. Centripetal acceleration or centripetal force always is towards the center of circular motion. Centripetal, this is centripetal acceleration. None of the other ones are. Good grief. So this is a weird diagram to say, what happens if an icicle is growing on your wheel? The centripetal acceleration is always trying to pull it to the center. The Greek or Latin, pater, I don't know how you say it, to seek or to strive after. It's center seeking. This is that centrifugal or centrifugal. This Latin word means center fleeing. Right? A fleeing fugitive. So when you have this motion, there is some force that is pulling you to the center in order to keep you in rotation. Do you see what happens the moment you delete that string? What did its motion do? What direction is this? What's that word? Tangential. It's in a circle. If I have a line that touches the circle at one point, that's tangential. You get rid of whatever is providing centripetal acceleration, your object is its inertia is gonna keep it going in a straight line. As soon as I cut that string, it's gonna keep going in a straight line, whatever direction it was facing. So I retry it. Remember Newton's third law? To keep this ball going in a circle, doesn't the string constantly have to pull it towards the middle? It's constantly changing its direction. Turn, 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 all the time. Every time that string pulls it to the center, the ball is also exerting an equal and opposite force. What is this? I don't remember exactly what this is called. It's not the discus. It's not shot put.
The hammer throw?
Hammer throw, is that what it is?
Hammer throw.
Yeah. It's literally a giant ball on a chain. Have you ever seen people when they throw these things?
Yeah. No, we're too poor to have it at our school.
I mean, they get tossed around, right? For them to be able to throw that, right, to apply that force, that ball applies the same force on them. That's why, you see how far she's leaned back? Because she's trying to hold back, like she's applying a force spinning it to keep it in circular motion, but it's pulling back on her. She's pulling inward every time. It keeps it in a circle. Well, the reaction is the centrifugal is the reaction force. This is why I say centrifugal is a fake force. It's not an applied force, it's just a reaction. It's Newton's third law. Right? Oh, have you ever guys done these? Oh, what's the one? Adventureland is a amusement park from where I'm from, Des Moines-ish, Iowa.
The scene from Sandlot.
Oh, you mean that flyover state?
Silly Silo. They got rid of this, and this was my sister's favorite ride, and they got rid of it like years ago.
Writing's not that easy, but Grammarly can help.
I hate the
This
Grammarly.
sentence is grammatically correct.
I'm not paying you.
So this is the silly cycle.
So, in the second section, you see the kids that have their feet up. They're not standing
Yeah, that's how they stand on the wall. Did you see it? Watch the floor.
None of them are touching the floor. How are they standing up? They're like glued to the wall.
So, I already thought that.
What happens in the silly silo is you get
Stays in the
spinning, and there is a centripetal acceleration. To keep you turning in a circle, the wall is constantly pushing on your back towards the middle of the rotation. Constantly. It's the only way you stay in a circle. Once you get to enough speed, as soon as you let the floor go, you don't actually fall. You stay there. The reason is you and the wall are squished so much. What prevents you from sliding? Friction. So the centripetal force is your normal force. It's normal to the surface. That means that you have friction. Once you have enough normal force, you have enough friction that as soon as you drop the floor out, you don't need the floor. You have enough friction to oppose gravity, and so you stay stuck to the wall and you're floating. Huh? Yeah, you are.
So if the world was spinning fast enough, we wouldn't need gravity.
Yeah. If you got the Earth to spin fast enough, your inertia would want to constantly fly off into space, but it would be balanced with the gravitational pull, so you'd be floating.
Wait, so you could kind of
We should try to do the math on that.
So I mean, I was kind of joking, but
Yes.
So if the force of gravity didn't exist, but the Earth was spinning fast enough, you would just be like,
Would it hold you out of the ground? Well, no. Because there's nothing to push us into the ground. Gravity is what's pushing us into the ground. If we got rid of gravity, nothing's pushing us into the ground.
with the Earth spinning fast. Oh, because then it would send us out.
Send us out. Because
Okay.
Yeah.
Remind me next class, we'll calculate, we'll see if we can figure out how fast would we need to spin the Earth to be weightless, to basically counteract gravity, or to have it be that gravity only accelerates us.
Like 1 pound.
Yeah.
That'd be insane. Look how high we jump.
So again, this is an example of,
Then I could at least jump in the 5 minutes.
guys, watch in the car,
Maybe.
watch the body, watch the driver when they make this turn.
They go.
That's what your body wants to do every time you turn a car. That's why you feel pushed to the outside, because your body's trying to go in a straight line. Yes. The reason that you stay in your seat is that there's a centripetal force, kind of comes from the seat, the friction on your butt, the seat belt, and if you go fast enough, you hit the door and the door pushes you. Those forces give you centripetal acceleration to stay in rotation.
So if I turn fast enough, I could just break the door.
Yes.
Awesome.
Awesome. We're gonna do
Now the thing you would have to do, you would have to be able to provide enough friction to sustain that turn,
Turns that you didn't just
to give you enough force to bust through the
You
door.
would most likely roll your car before that would happen.
Yeah.
yeah.
That's true.
Yeah, you go,
Really,
you'd
really
flip it big
low
time.
That's not Plano.
That has
This centrifugal force is on the door. It's why you feel pushed outside. You're not getting pushed outside, you're getting pushed inside, but your reaction to getting pushed is on the door. The force causing your motion is centripetal. This is just Newton's third law. It's the reaction. It's what you feel. Force is in the same direction as motion. That should make sense. This force is in the same direction as motion. It's inward, center-seeking. It's constantly at a right angle to the path of motion. If you have an angled force, part of it speeds you up, part of it keeps you turning. In this case, part of the force is slowing you down, part of it is keeping you turning. Now, this should look familiar. This is just Newton's second law. F equals ma. You just rearrange it. Well, if I'm turning, we call that centripetal acceleration. So we have a new version of Newton's second law. It's not linear acceleration. It is specifically the acceleration to turn. They call it AC. So centripetal force equals mass times centripetal acceleration. I don't want you to worry about that. Centripetal acceleration is a change in velocity over time. Well, wait, how is your velocity changing? It's just turning. Remember our arc length that we talked about? They basically take the two vectors and say your velocity changed by a certain amount. That's the change that happens. This is what we're going to get to. If you do all this math, don't worry about this math. There. That's the conclusion. All this math is to show you, hey, if you change the direction of my force, I have a delta V. That delta V is my arc length over the radius. Do a bunch of algebra. Don't want you to really worry about that. And the end result is that the centripetal acceleration is V squared over R. That's the kind of big takeaway. I think I'll pause there. Cool. We're going to finish up with, okay, what do we do with this equation? Centripetal acceleration is equal to my velocity squared divided by the radius of the circle that I'm turning. Then we're going to use that, and we will be able to do math and calculate. All right? So again, I'll pause there. We'll pick up next class with centripetal acceleration and actually be able to do some calculations with it. It'll be easy, but it's just tricky to shift your mind from linear motion. We're all really used to that. We know that. We aren't as comfortable with circular motion, and so it's hard to learn this because you don't have as much background knowledge or like experience to try and make sense of this stuff. So we'll wrestle through it. It'll be fine, but don't be frustrated if it doesn't click with you immediately, because it's not supposed to. Yeah, I'll pause there. I want to do that calculation. We'll do that next time about the Earth.